Swayam Prabha. Digital India. Educated India.
So now we'll open the I think I need to open HA1 first because one of the problems we could not solve because of time. All right, so I think we didn't go to the number 4, right? You did only 1 to 3. So let's, because we didn't cover GA at that time enough. So I want to solve the same problem here using binary coded GA, okay, which we introduced today, actually yesterday, but we did a bit theory today. We want to have 2 decimal places of accuracy for variable x1 and 3 decimal places of accuracy for variable x2. How many bits are needed? Okay, for x1 you see the lower bound, upper bound, -2 and 8, and for x2 is -6 to 6. I'll use the board, not for this problem, but let's say I've got another problem where x1 goes from 0 to 5 and x2 goes from -1 to +1, let's say. And I want 3 decimal places of accuracy here and 2 decimal places of accuracy here. Means when I look at x1, I have 0 to 5 is my range. I want to have intermediate points. So every binary string is going to map here, right, in this decoded space. The distance between 2 should be 0.001, 3 decimal places. Then only I can get 3 decimal places of accuracy, right? And on x2, the distance should be 0.01. How do I find how much string, how many bits do I need? Remember the formula we discussed was b minus a, b is the upper bound, a is the lower bound, divided by 2 to the l minus 1. This is basically this difference. If this is your A, this is your B, and you are choosing L bits for that, x1, this should be the precision, B minus A divided by 2 to the L minus 1 gaps. There are 2 to the L points, but gaps are 2 to the L minus 1, right? So this is the delta. So this should be less than equal to delta. That delta is either 0.001 or in the other case 0.01. So how do we find x1? 5 for x1, 5, b is 5 and a is 0 divided by 2 to the L, let's call this L1 because for x1 minus 1 should be less than equal to 0.001. Can you solve it to find L1? Okay, L1 you will find a non-integer, but then you take to the, because it is less than equal to, so you take to the, because when you do this way 2 to the L will be greater than equal to 1 plus 5 over 0.001. So now you do L1 greater than equal to log to the base 2 1 plus 5000. So this when you compute you will probably get some integer, so some non-integer. So let's say I don't know what this is, but 238. So if that's the case, it has to be greater than equal to 10 to the 238. So what you will choose? 11. 11 should be minimum. That will give you this kind of precision. Same thing you do now for x2. So x1 may have 11 bits, x2 may have 9 bits because I have less precision I'm wanting here. So you can try that. So that's the first A. Any question? Very simple, just simple exercise for you to see how in binary coded GA, we don't use them anymore, but this is a good idea to see how they used to figure out how many bits are needed. And we have a code that does that too. Okay, second part is, can you mark the region represented by the following 2 schemata? So let me do another one, not just this one, over this side. Okay, let's first do a single variable. So let's say I've got, how many bits I've got? Here I've got 6 bits. Let me do with 5 bits. So with 5 bits, this will be 0000. and its decoded value is 0, right? To the base 10 is going to be 0. So this is 0. How is the last one? Will be 31, right? So this will be 31. And then you have 1, you have 2, you have 3, all of them. You have 30 here. Okay. Now we talked about this. Let's say my schema is, I don't want to do the exact one. So let's say I do another one. 0, 1, star, star, star. Can you identify what region does it represent? Yeah, 0, the middle one. So 15, let's say starts here, 16, here there is 14, okay. So 16 will be with 1 at this place, right? That will start with 16. So 15 is the one that 0 ends. So 0 will go from here to 15, okay. And this one is the next half. So it is going to be 8, somewhere there is 8 to 15. This is the region that's represented by this schema. Is that okay to everyone? This 0 means the left half. This 1 means I'm now splitting the left half into 2. 0 here will say left half of that. 1 means the right half of the left half. Okay? So it will be 1/4 of the entire space because I have specified 2 bits. It will be 1/4 of the entire thing. So it will go from 8 to 15. Okay? That range. So you can mark that. Now let's say I've got 2 variables. So this is the first variable x1 and the second one is, let's say, 1 and star, star, star. So now I have x1 here and I have x2 here. Okay? Let's say I have 1 less here. So I have 4 bits here because as you see x1 can be different than x2 number of bits. So with 4 bits I'll have 0 again, which will come from all zeros, and this all ones is going to give me what? 15, right? 15. And somewhere here there is 7 and then 8. Okay, so this one we've already figured out this much. And this is for x2. Which region does it represent? The top half, because it's all from 8 onwards. So it's top half, this part. Now this is AND, x and x1 and x2. So which part will that be? This part. This is the region. This part comes from x1, this part comes from x2. So this is this schema represent this part. So I want you to mark on a square like that whatever you found here. So let's say you found some bits and here you found some bits. You get this entire thing and mark which region corresponds to these 2 schema. They'll have 2 different regions to mark. Okay? And for this problem 3, I think you may have done it already. What was it? There was a line like this and I think there was a thing like that, right? And this one goes, the bounds goes like this. Here was the optima. You can see both the schema that I have given, you will mark it, they will be rectangle, okay, or maybe square somewhere here. Is it any of this schema covering the optimum? You will probably see no, it's not covering. It's not part of the question, but I'm saying as an extra work, if you have time, can you identify the same area schema that will occupy the minimum? That will be an interesting study, right? So these 2 schema that I have given here, they may not include these points because they could be somewhere here or could be somewhere here. I don't know where they will show up. They could show up over there too. Just try and see where the schema is. If not, if none of them this, that means they are not important schema, right? The GA will not get to the schema, not fix up with 1 and 0 at the first 2 place and 0, 0, 1 for x2 at the first 3 places. It's not going to do it because it's not an interesting region if it's falling here. If the same area, that means the same number of bits, fixed bits, if you can find something here, okay, that's the schema that GA is going to give importance to because more and more of these points from this other region is going to go there. Now, if you try to solve this problem with binary coded GS, this is something you can observe. You can track how many of my population members occupy this schema. And you will see that starting with very few, it's increasing. And that's a proof that GA is doing something right, that it's pushing points from all other schema. So all others are its competitors, right? These are all its competitors. All the others that are not this are its competitor. You will see that their number is reducing and this guy's number is increasing. And that's one experimental way of proving that GA is doing the right thing. But this you can only do for binary coded GA. But I'm not keeping that as mandatory because that's a bit of work for you to figure out. But if you have time, do this. It's a very interesting exercise. This kind of gives you good idea of how binary coded GAs work. Make sense? Okay. Any question about the schema stuff and the how to get the number of bits? Simple exercise, right? All right. Now I go to HA2. So solve the problem 4 from HA1 as a part of HA2. Okay. Now come to HA2. First one is about constraint handling. We talked about today how to handle constraint using the penalty parameterless approach. This one will help you do that. So I have given you here 7 points. You see, these are 7 points, 2 variable points, x1, x2, x1, x2. You can plug in here. You can see if they are feasible. Okay. If not, so when you check the feasibility, you also have to consider each of these as a constraint. So let me explain. Oh, I could have taken that example, but it's okay. So let's say when I have 0 less than x1 less than 5, it's a variable bound, but I can convert this into 2 constraints. One is minus x1 less than equal to 0 and x1 less than equal to 5. You see, this can be converted into 2 constraints. So I already have 2 constraints, G1, G2. You can call this G3, only this part. You can call it G4 minus 5 and then G5, the other constraint for x2. You can also convert the variable bounds for x2 into 2 constraints. This is not the exact constraints I have there, but you can do that. So there will be 6 constraints total. And now you need to compute the CV. Remember the way you do CV? CV is the sum of bracket operator for all Gj normalized. You will have a good exercise with this. So j going from 1 to 6. Now how do you normalize this one, for example? I don't have a right hand side value other than 0, so I shouldn't divide by 0. So normalization of G3 in this case is going to be whatever is the maximum value of x1, which is 5. 5, usually we do 5 minus this. So you can do 5 in this case. Okay, so that's your normalized with a minus sign. And G4 normalized is going to be x1 minus 5 by 5 because we divide by the fixed number. Okay, so this is how you normalize. And the other 2 constraints, there is a right hand side value non-zero, 16 and 3 that are given, so you should divide by those. Okay, and then check if this is greater than 0. This operator does that. If it's greater than 0, it's the positive value you have here. If it is less than or equal to 0, you put 0 here. Okay, so I think it's best to do in an Excel sheet. So I will now show you the Excel sheet. This is how I have done it. Maybe you can also follow the same. You see, this is not the same problem. I am showing you for another problem just to give you an idea. So there are 7 solutions here, also 7 solutions. I hope it's not the same problem, but even if it's the same problem, doesn't matter. So you have x1 vector and x2 vector. So this is x1, x2, one solution. Now you see G1 you compute. So G1 is this divided by the constant, and then G2, another constraint I put in, it comes from x1, x2. Then you have G3. G3 is simple, you see, variable bounds. G4, another variable bounds, G5, G6. So these are with x2 and these are 2 with x1. And then you compute the CV. I'm little rusty in my programming, but so I did like every one of these constants. So if you look at this, all the constraint values are used. If any of the constraint values is greater than 0, I take that value, otherwise it's 0. Then go to the next constraint, next constraint, next constraint. You can maybe some way you're a better programmer in Excel, you can add them in a loop. Okay? So once you do that, you get the overall constraint violation. If this overall constraint violation value is 0, means every constraint is satisfied. So all the thing here 0 you see, this one's first one, second one, and this is the fifth one, and this is the seventh one. They are feasible in this particular case. All the non-zero ones, positive ones, are going to be infeasible. So remember that plot I had, there are 3 feasible and 3 infeasible. How did you get the F max? You need to now evaluate every function. So this is a different function, you evaluate. Out of all the feasible ones, these 4 ones, which one has the highest value? So I wrote a simple code here to max of, if this is 0, I take that value, if this is not 0, I put it 0, and then I take the max of that. It turns out for these feasible, these 1, 2, 5 and 7, if I look at the function values, okay, you see this is the highest. So that's your F max. So you put it F max over here, and now for all feasible solution, objective function is same as fitness. You see, all feasible objective function is same as fitness, right? And for all infeasible solutions, these ones, you have to add 270 with 101 and you get this, 213 with this and you get that. So all the infeasible ones, you have to add the function value with the F max. So that's how you get your fitness. Is that clear? You have to probably refer to that constraint handling slide that we discussed. After you get that, can you rank them? So obviously we are minimizing the fitness, so which is the best one here? Best one is 21.25 out of all of these. Second best is 30, third best is 47.5, fourth best is 101, fifth is this one, sixth is this one, and the worst is this one. So now if you do your tournament selection with this, all the right things are happening. If you pick one feasible with one infeasible, feasible will always have better value. If you take 2 feasible, the one with the smaller f is better. If you take 2 infeasible like this one and that one, the one with the smaller constraint violation is going to win. Everything is set up in that mode. So this ranking will work. You can also do tournament selection with this ranking. Does that make sense? I think it's better to do in this Excel sheet. Be careful in typing all these formulas and everything. Okay, you will have a good understanding of how these constraint handling works. Any question? No? Okay. I think these are small things that will give you a little more perspective to what's going on in the lecture, right? Next was, so that's the first question of HA2. And I've given here a hint of how you, oh, it could be the same problem I've solved. Okay, no problem. How to normalize, I've actually explained. Now, second one is about multi-objective. Second and third for multi-objective, basics of multi-objective. So, I give you this Z. You see this figure? This is the feasible Z. This is objective F1, objective F2. Feasible space. I put the grid behind because it may help you. Oh, I have not talked about cone domination. Okay, that's very simple for me to say. Let's finish this one. So, this part, I'm tangled here totally. Okay. The last part is mark, first let's do this. Mark the standard Pareto optimal front using 90-degree cone. So, let me talk that first. So, it's a small thing. So, let us say I have a point here and I have F1, F2. What did I tell you? This point A, if I have a 90-degree cone, if I call it 90-degree cone or first quadrant, this point is better than any point here, right? In some sense, we say this point dominates this entire region. Dominates means this is better than any point over here. That's the usual Pareto definition. Is that clear? And for weak, this point is better than interior. So if I have any point over here, this point is not better than that, it's equivalent. But if you're just slightly away in either way, then A is better than that, then you have weakly Pareto-optimal thing. Okay. Now the proper Pareto is also known as cone dominations. I forgot, it was there, but I forgot to mention. What you do is you take this line and you widen it with some angle. You widen it. Then what happens, you're saying A is better than even these points, all of these region here. If you do that, what happens? So let's take an example. I will not take this same example, but let's say I'm going to take that same one that I had. Okay. First, when I do the 90-degree cone, I'm saying A is better than any point here. But if I go to its mirror image on the other side, third quadrant, any point here is better than A, right? So if I take a point here, if there is nothing here, this is Pareto-optimal, so the entire thing was Pareto-optimal. I use the same logic and say that this point is better than anything over there. So if I take the mirror image, I have to cross this line that way, I have to extend this line this way. Any point here is going to be better than A. That's what it comes, right? So if I can do both ways, right? So let's do this way first. Okay, I take this cone and put it here. So that's why the grids are there, right? You can put it this way and that way, which means this point, if it's there, it's better than any of these points. Okay, so fine, that point can be there. Now let's come over here where this line is a tangent, and then this cone I am putting again. Same cone, I am putting it here at this point. This means this point dominates this entire thing, which means this point is also better than that point, because this falls inside the cone now. I have expanded it, I broadened the cone. So that means this one cannot be Pareto-optimal anymore with this definition. Okay. So if it's tangent here, it takes care of all of these. If you're here, draw parallel, that still makes this one thing, but then this point will also include that. So if you can come to the tangent line, then that's the starting point of this Pareto-optimal set. And if you come with this tangent line, wherever that is, and that's your cone, so now this point dominates all of this part, which means all of this is gone. This is also inside that. So any of these points cannot be Pareto-optimal anymore. But any point in between this, if you do a cone, it's not deleting any of these. So they stay. In other words, if you go to the opposite side, there is no point here to this. If you go this way and that way, there is no point here. So you will find that to this region, there is no point that dominates it. If you apply the inverse part of it here, so this line coming and this line going, you see there are some points, which means this point dominates that. Okay, so this cannot be. So you can play it both ways. You can take these, I call this omega, and this we call omega dash. This is called the anti-inferior region. You can take that part and apply to each of the Pareto points and see if there is any point there. If there is some points, then this cannot be. So you can apply that and you will find that this part is not covered with any other points in this omega dash image, which means that's the Pareto-optimal set. So can you do this for this problem? I've given you the cone. You can count to get, so the grid is there. So if we go 3 units on F1, you go 1 unit down to get this bottom line. To get the top line here, you go 3 units up and 1 unit on the left. So these are not arbitrary lines, these are well-defined lines. So you can now take these two lines and put it anywhere you feel like, this pair. You can take it anywhere, count the grids and see, what if I get the omega dash of it and apply at each point and see if there is any part of this feasible region that falls inside here. If it is, then that point A cannot be Pareto-optimal. Try that exercise. This will give you a very good idea about multi-objective Pareto optimal definition. Of course, you should not try any points here on this part because those are not, it has to be part of the original Pareto set. So you go with this boundary and then try that. Same thing is I've changed the cone here to a smaller cone and apply the same logic and see if you can figure out which part will be. So this will be 3 figures like this, one for the original Pareto set, one for this cone on the left side, one for the right side cone. Can you do that? Okay, this will give you a good exercise. That's the second. And that last one is I've given you some numerical problem here, x cube plus x square. There is a correction here. I have to remember what was the correction. X has to be greater than or equal to 0. So I forgot to change this, but f min search has to be f min con. Can you note this down? And we have to add a constraint. Constraint says x has to be greater than or equal to 0. So third problem, minimize f1, which is x cube plus y square. Second objective is minimize f2, which is y square minus 4x. Subject to, there is a constraint that says x has to be greater than or equal to 0. I think so. So that's the only constraint you have. So because of this constraint, you need to use f min con. You cannot do f min search. Okay. So, and now you're going to use weighted sum. So how you do weighted sum? So weighted sum objective is going to be, if you use W1, it will be W1 x cube plus y square plus W2 y square minus 4x, and W2 is equal to 1 minus W1. So you basically choose W1 and I've given you 3, 4, 5 values, 1, 0.75, 0.5, 0.250, 5 values. So first you use W1 equal to 1. So this becomes 0 and you optimize this function using f min con, this code, the only with this constraint. And then you use 0.75, then this will be 0.25. Then you use 0.5, 0.5, then you use 0.25, 0.75, then 0 and 1. Okay, 5 times you are going to run f min con. Okay, and then you are going to find 5 optimal solution. Every time you do this, so when you do this one, you are going to get a x star, y star, right? And also print out corresponding f1 star and f2 star. Not from here, but for these compute f1 star, put x1 star, x star, y star, x star, and you get f1, f star, f2 star. So print this, okay? Print these 5 values. And now you can go and plot. So plotting will be done on f1 and f2 scale. These 5 f1, f2 that you have, plot them like a circle, okay? And you see what you get. I'm going to show you the result, but what is expected. So here is the code. So declaring the text with the 2 functions, and then these are the MATLAB commands, but I'm just showing you. So what it did is define the W1, and W2 is 1 minus W1, and W1 is defined, W2 is also defined. Now initial point, you can use 0, 0. I probably haven't mentioned, but you can use any initial point. So just fix it. And then the lower bound, upper bound for 2 variables. Yeah. So here, I think the x1, I need to look into the code. 1 second. I need to look into that constraint. What I used as a constraint. Where is f min con? Here. I didn't put any constraint. Wait a second. How is it possible? Okay, let's see the bounds. Maybe I handled it with the bound. No, both are going from -1 to 1. Did you run it, Dipanshu? I thought I had to fix that. Here, low, high I put. Because, okay, let me run it. Let me run. Can I run this in MATLAB? Yeah, okay, run it. Okay, here are the results, right? It's running. Because there was this square root problem if I have negative values. That's what I thought. But how did it take care of it? It's been a while that I solved it. Let's see. Low, high, and both low and high were going -1 to 1 and -1 to 1. So both can be negative. That's fine. But the issue was, oh, okay. We fixed it this way. Not with the constant. Sorry, this is what we did. We just did it with variable bounds. Let's do it that way then. So we are not going to do this, okay? We are going to rather put a bound on variable. So -1 less than equal to x1 less than equal to 1 and -1 less than equal to x2 less than equal to 1. So we are kind of bounding the search. Otherwise, for w2 equal to 1 and w1 equal to 0, you see x can go to negative infinity. But sorry, x can go to positive infinity. So that's going to minimize. So it's unbounded search. So we bounded it. Okay, that's how we handle. So add this one. Now if you do this, f-min search cannot do it. F-min search cannot have lower bound, upper bound. That's why you have to go to f-min con. So there is no constraint you are putting. You are just putting variable bounds. And that's why we have no constraint. You see, here I would have put the constraint function, but there is no constraint we have. But we have variable bounds, so we put low, high, -1 to 1 and -1 to 1, and we put it over here, low, high, right? So the search is restricted within this -1 to 1, -1 to 1, so it's not going to go to infinity or minus infinity anywhere. So then, you see what happens is, I'll show you the plot. You only see there are 3 points. But I should have got 5 points because there are 5 runs we made. What happened in this case, and I want you to understand this. So here, for different w1, these are the x vector I'm printing, right? Look at these are the x vector and this is the corresponding f. But I also should have plotted the PO. Okay, let me plot the PO. Yeah, here the PO. PO is, my PO set is, come on, PO set is, how do I set the PO? It's the, x1 star, x2 star, and the f1 star and f2 star. Okay, so there are 4 columns. Okay, and here is the PO set. PO set, here I saw it. Where is it? Did I just saw it? No, where did it go? Okay, let's run it again. So maybe I can. Yeah, here I'm setting up, but let me also print the PO. So before I plot it, can I add something here? PO. I'm going to print out the whole PO matrix next time I run it. Run it. Oh, here it was. No, now what happened? Here, it took some time. Okay, so here is my final 5 solutions. So first one is x1 0, x2 0, and the corresponding f1, f2 0. Can we justify that? W1 equal to 1. So when W1 is equal to 1, this is not there. If I minimize this function where x goes from -1 to 1 and y goes from -1 to 1, and there is no cross term, we're just minimizing this function, what should be the value of y? Square. So always positive. So the minimum will be 0. So y will be 0. So that I agree, y will be 0. And x1 now, x cube is like this, right? And you are going between -1 and 1. So when you minimize, it's going to go to -1, right? x1 should be -1. Why am I not getting it? It's giving me 0. Okay, there is something wrong. Yeah, xv1, xv2. Okay, for first w1i, w1 is defined here. Here, first one is 1, okay, and then w2 is 1 minus w1. Okay, so cube square, cube square, square minus 4. So when I minimize this, x1 should go to minus 1. I get 0, 0. That is strange. F min con, objective function, 0. I'm starting with 0, 0. And it's kind of stuck there. Why? This should be minus 1, according to me. Unless I have it's giving me values. PO. Let's try to run.
Because it's a saddle point.
No, but minimization, it should, it's minimizing. It's not finding the saddle point. No, not there, not there. I'm going to print out this one.
Gradient is 0.
Gradient is 0, but I have allowed it to go to minus 1, so it should find better solution. That could be a problem with the algorithm, but it's such a simple function, it should not. Yeah, 0, 0. Okay. Let's start with some other point. Maybe we do with, let's say, point, so minus 1, right? Let me start with a negative. Use some problem information. Negative, let's say, point 3 and 0, okay? Let's see what happens. Is it running? Okay, it ran something. Yeah, now it goes to minus 1. So it's probably some condition, it's a saddle point, right? The gradient is 0 here. So the gradient based methods have that issue, right? Because this is definitely not the minima. So minima of this function should be this. But because I'm starting from such a point, let's start with the point here. Let's see if it can avoid. So I'll do plus 0.3. See if it does that. There's always things to learn in this. 0.3. Now you see it goes somewhere else. 0.1798. That's not good. Oh, this is 10 to the minus 3, which means it's almost 0. So starting here, it's just going here and getting stuck. But if you give it here, then it finds a slope and comes over there. But you see, in constraint problems, there are bounded problems, it should not work with gradient equal to 0. Should not be its termination condition. Because that is with the unconstrained problem. F min search I would have understood. But this one it should not. It should find the minimum during this, in this space. Yeah, so these point-based methods have lots of issues. So now I doubt the other ones also. But other ones seems to be going. Okay, so let me start with that minus 0.3 for everyone. And let's see whether we get the same thing or not. Then we can use that. Okay, and I can make that comment now. So that we get some nice crisp results coming here. Okay, here. So now I got minus, yeah, other results are the same. Okay, so it's an issue with the initial point, and I told you that these point-based methods are so sensitive to initial point. Okay, so this is correct answer. Okay, and this is the F1 value, and this is the F2 value. Okay, and then this is the W1 equal to 0.75, F1, F2, and 0.5, F1, F2, 0.25, F1, F2, and 0 point F1, F2. Why these three values are the same? I've got the same point, 1, 0, And when I plot them, that's why I have 3 points. It should have been, oh, this one is gone. Oh, this one has come here now. Okay, yeah, that's expected. And these two are over here. So why all the 3 runs have come here? Like these 3. It goes to 1, so the F1, F2 is 1 and minus 4. So F1 is 1 and F2 is minus 4, which is there. All 3 points for W1 equal to 0.5, 0.25 and 0. I think those are the last 3, right? They are all coming out to be the same point. Why is that? Here is the reason. So this is not in scale. This is minus 4 to 4 and this is minus 1 to 1. So if I do them, so this is a width of 2. Here will be width of 2 is minus 4 to 2, right? So if I do this scale properly and if I join a line, can you imagine a line which is with a 45-degree line from here? It's going to go to 2, right? Is there a way to add a line here? But anyway, so this will go to this, to 2, right? That line will be tangent at this point. If you think of a line that's same width, 2 here, and we are going to go 2 width, so it's make like a square, because this scale is quite large than this scale, right? So any line you draw here is not going to be the exact line. So if you think of this being same width as this, then this will be the 45-degree line that goes from 1 to minus 2 over there, and this point is going to be tangent. So what we end up having, let me do it here so you will understand. So these simple problems make us make the ideas very clear of what's happening. So what I have here, if I expand that part, this is my Pareto set. Okay. Here minus 1 to 1, this is F1 and this is F2. I think this goes to 4 or plus 4 or minus 4. This is plus 4 to minus 4 here. 4 minus 4. So if I do the same scale, this is actually 45 degrees. So that means this is 1, 1. Or if I can say also 0.5, 0.5 slope, which is coming from W1 equal to 0.5. Remember what I told, this is W1 and this is 1 minus W1, right? So if you choose 0.5, you have a uniform slope, which is 1 slope. Slope equal to 1 means 45 degree. In this scale, this is the 45 degree. And remember what I said, once you choose W1, W2, when you do weighted sum, wherever the line is tangent to the Pareto set, that's the point you will get. So this is the tangent point, not anywhere here, and we got that point. So W1 0.5 is fine. We are expected to get that. Now let's choose W1 0.25. What will be the slope? Slope is W1 by W2, W1 by 1 minus W1. So when it's 0.25, this is 1 minus 0.25, 0.75. So this is 1/3. So that means if you go 1 this way, you will go 1/3 that way. So if you go like 1 this way, you will go 1/3 this way. So I need a slope that is like this. It's more like this. So which means I'm thinking of a slope that is more than that, like this, right? When 0.25, where is that going to be the tangent? Because this is your space. Okay? So where is this line tangent? This line is going to be tangent probably, have I got it right? I thought it should be the other way around. W1 given me, 1 second. W1, first one is 1. Yeah. The fourth one is 0.25. Yeah. So, 0.25 by 0.75, 1/3. 1/3. So W1, oh no, I did the wrong way. W1, if W1 is 0.25, so I'm going 0.75 this way. Let me see how to work with this. Yeah, 0.75 this way, not 1/3. So if it's 1, I'm going to go 3. I did it the wrong way. If I go 1, I will go 3. 3. So it will be much lesser slope. It will be a slope like this, because 1 unit I go 3 unit this way. This is 1 unit, I go 1 unit that way. So 1 unit, 3 unit this way. So it will be lower slope than this. So not that. So if I have a lower slope than that, where is this tangent? Same point, right? Because here itself is 45 degree. If you do anything less and there is nothing here, so it's the same point you are going to be tangent. It's not going to be tangent, but it's going to be the best point that is coming there, right? Because there is a kink here. So this is all going to be below it. And then when it is 0, then you have horizontal, which is this line. Also, this is the best point with respect to that. That's why all of 3 are coming to the same point. It works with that concept. And then when you have 0.75, then it is like when you go 3 units, you go 1. So if you go 1 unit, you go 1/3. So now you have a bigger slope, and I think somewhere here is the tangent if you go to the slope, and that's all you get. And when it is 1, then it is infinite. You have a vertical slope, which means this point, and that is what we get. Now the big question is, can I get anything here? No, you can try any W1. I mean, this could be an exercise. You can just try changing any of the W's here. Yeah, you change anything you feel like between 0 and 1. You are never going to get anything on that part, and that's a good exercise. So that's why I put it here. You'll never get anything in this non-convex part, but convex part, by putting more and more points, W's above 0.5 to 0.75 to 1, you can create more points, and you'll see you'll get lots of points here in this part of the thing. So it's a good small exercise for you to see how the weighted sum works. Okay.